Hello, everyone. Yeah, I hope you had a good lunch and you're not too tired. So I'm, for the very first time, speaker at Jfokus, and it's fantastic that my talk was accepted, and I'm having the opportunity to be part of this fantastic conference. Yeah, this talk is all about in-memory computing, the big picture, and I try to introduce you to in-memory computing with a beautiful video that shows modern applications. And of course, we are all Java developers, and we want to develop all these modern applications with Java, of course. And memory computing is super important for all of these modern applications. It's because of with in-memory computing we have the chance to build very innovative applications, new innovations, products and solutions, giving the users a better user experience, saving resources, and for developers it should be higher productivity, and of course we also use in-memory computing for saving costs. And it's a super interesting study from Amazon. They found out that 100 milliseconds of latency cost them 1% in sales. So latencies are very expensive, so we try everything to get best possible performance and try to eliminate latencies. And there was one guy at our booth, and he said, we urgently need performance, we need the best possible performance. My name is Markus Kett, CEO and co-founder of MicroStream. We're developing with Java for almost 20 years now. So we contribute to several open source projects. We started with creating a development environment. So our goal was actually to build a kind of like Visual Basic for Java. So, and to bring all these 4GL applications, legacy applications to Java, enabling 4GL developers using Java, a great programming language. We built the user interface builder for Swing, then we migrated it to Vaadin to run it in the web, and everything worked great with our GUI builder. But the problem was, as soon as we want to show data on a screen, then the horror began. And all these 4GL developers had to deal with Hibernate, and so they were not able to do that. So it was too complicated for them. So we tried to improve this and worked for many years on the JBoss Hibernate tools for Eclipse. We tried to improve the tools, increase the Hibernate tools, saving bugs and something like that. 5 years later, then we recognized, so we cannot really improve this, because of the core problem, and this was the reason why we, worked on MicroStream. Now open source MicroStream. It's also an open source project. This is something about my background and my background of my team. So you can also visit our booth at the exhibition hall. MicroStream is now also a part of Micronaut, and it's integrated in Project Helidon. So now we contribute to various open source projects. About the agenda, first of all, I like to talk about why memory computing, why is in-memory computing that interesting for us? Of course, we also should talk about the latencies. Where are actually the latencies? Then I like to talk a little about traditional Java persistence, local caches, distributed caches. And this talk is about also about the buzzwords. It's because we use all these buzzwords all the time, and in meetings I saw that many people don't know actually the differences between all these techniques. So I like to compare these solutions and to give you an overview and to make better decisions to, what fits best for your use case, and that you'll be able to make a good decision for your solutions. I show a demo, and of course we have some time for Q&A. So in-memory computing is actually everywhere. So we use in-memory computing for accelerating software. Databases, of course, use in-memory computing, but also the devices use in-memory computing and storing data in memory because it's that faster to deliver data faster. And here are some numbers from the internet, of course, that should show how fast actually memory computing is. Here we can see if you have access to memory directly, so everything that is executed in memory, and we read from memory, then it only takes some nanoseconds. And mostly it's not really clear so how big these numbers or small these numbers actually are. So when we compare a nanosecond with a microsecond or a millisecond, then we talk about a factor 1,000. So in comparison to a microsecond, a nanosecond is 1,000x faster. And when we talk about nanoseconds and milliseconds, then we talk about factor 1 million. And when we have access to disk drives, then we talk about milliseconds. Database access time, we talk about milliseconds. Access to memory is almost 1 million x faster, or up to 1 million x faster. This is incredible. So actually, we should use this all the time. But the problem is, of course, memory is expensive. So this is the reason why we cannot use in-memory computing all the time. Here again, some numbers, DRAM. When we talk about in-memory computing today, then I mean mostly DRAM. There is also persistent memory, which is very interesting. Databases mostly must have access to disk drives. Then we talk about microsecond query time, or with SSD drives, or mostly milliseconds. So what about Java? How fast is in-memory computing with Java? What do you think? Is Java super fast, or is Java actually not that fast technology? Who believes Java is super fast and suited for in-memory computing? Not that much, okay. Yeah, my investors also, so because we run a new startup, and investors always ask the question, is Java actually still suited for modern applications? Should we invest really in Java? So let's see, during the talk, I hope I can answer this question. I believe Java is super fast and the best technology, and it's not only because I'm speaking at the Java conference, of course. It's really true. But if Java is that fast, so we have a JIT compiler. The JIT compiler accelerates your application tremendously, then it's not that slower than in comparison to a C program. Maybe C is a little bit faster, still faster, but with our JIT compiler, Java is incredible fast. So the question actually is, where are the latencies? Why are database applications mostly slow? Who of you, by the way, develops database application or data-driven application? Okay, yeah, many people work on database applications. So are they incredibly fast, or do you have issues with performance? Who has performance issues? Sometimes. Okay, a lot of people. Okay, that's the best question. And this is the core question, by the way. Let's have a look on the architecture. This is a common application. We have an application or a microservice written in Java. Then we have some data objects in memory. We have the JVM, we have a virtual machine, and we have a database. So first of all, I like to have a look into the database system, because mostly the database is a black box. So nobody thinks about what happens inside the database. We just send an SQL to the database does something and submits a result set. But actually, what happens in this black box? Here also we have business logic sometimes. So the database vendors, they tell us, write your business logic with stored procedures. Good idea. Who uses stored procedures for database programming? Not that much, okay. Of course, we are Java developers. Then we have also memory, of course. So database servers need memory. Why actually need database servers memory? Because we just send an SQL, they give me a result set. Of course, databases also use caching to be able to deliver the results sets faster. So database systems also use memory computing. Then we have the database system, the database management system, of course, that is responsible for everything in terms of querying data and caching and something like that. And of course, we have storage. This is very important. It's because how actually do databases store data on disk? Sometimes the vendors decide for human readable formats like JSON, but many database systems just use binary files or store data in binary format on disk internally. With cloud database solutions, of course, we have storage, and mostly the storage is anywhere. So we cannot be for sure that the disk drive is directly at the same machine where the database system is running. So perhaps there's wire between the database server and the storage. Okay, so this is important for later. So looking into the inside the database. So let's go back to the black box. With Java, everything is fine. So we are keen on object-oriented programming and clean code, and yeah, so this is important for us. And everything in Java is an object, of course, which means data are also objects in memory. Everything is fine, but as soon as we want to store data, then we have to deal with relational databases. And they, unfortunately, work fundamentally different from Java because they are not able to store objects. So this is, from a technical perspective, not possible. So we are in trouble, actually. Then what's about the NoSQL databases? They now work fundamentally different, but what's actually the biggest difference between a relational database and a NoSQL database? I would say it's the data structure or format. The relational databases, they store data in columns and in tables and columns. And NoSQL databases introduce new formats like JSON, XML, key value stores, time series, or graphs, or the older databases, the so object-oriented databases in the 1990s. So different data structure, but are these databases able to store objects? No, they are not able to store objects as they are used in Java. So we have the same problem here as well. And this is the reason why we always have to build our object model around the database. So we have to build our database applications in Java around the database. So to solve this problem, and by the way, we talk about impedance mismatch here. So there are various impedance mismatches. Why do objects and the Java object model does not fit to the relational model? Because of there are no subtypes in the relational model. The object model is more granular than the relational model, and so on. So there are various impedance mismatches, and this is the same problem with NoSQL databases. Of course, we can read in the internet about this topic. For instance, great article even Wikipedia about impedance mismatch. As I mentioned, the NoSQL databases introduce new data structure. They are all incompatible with the Java object model. So how can we fix this? Of course, we have object relational mapping. So when Hibernate came up, so it was much more convenient to store objects in a database. And the idea is actually we want to store objects. Actually, we don't want to deal with the database. So abstracting the database to be able to build the entire database applications with pure Java. So this is the idea behind this. So we have to add object relational mapping framework, like Hibernate is the de facto standard here. Who uses Hibernate, by the way? Great. So this was also what we have used for many years, of course, and tried to improve the tools for Hibernate. By the way, you can check out Rapid Clips. The IDE is called Rapid Clips. It's open source. You can download it for free with improved Hibernate tools. Is Hibernate actually fast? Who has performance issues with Hibernate? Yeah, many people, of course. It is not that fast. The question is why? Because of this object relational mapping behind the scenes, we need through every single read and write, we need an object relational mapping or a creating of SQL code through every single read and write. And this is expensive. These are one of the reasons why we have latencies all the time. And when we measure the query time, then we have measured it, and we recognized it often doubles your query time. So no matter how fast your database is, but your database do not deliver objects. So you have the object relational mapping framework has to generate objects behind the scenes, and this sometimes doubles your query time. It's incredible. So to accelerate queries, Hibernate queries, we just use a cache. Because we know a cache means we store data in memory. And so we don't need to execute a query. Database does not have to execute a query. We just read the data from the memory. So do you think a local cache like cache, so there are many solutions out there, how fast is Hibernate caching? Nanoseconds? No. But why? We read data directly from the cache. It's because Hibernate serializes the objects into the memory, and when we read data from the cache, we have to deserialize it behind the scenes. And this does not take nanoseconds. This does not take microseconds. This mostly takes even milliseconds. So milliseconds, even when we read data from the cache, that's not really super fast. But this is the reason why we mostly need a local cache, but the performance is still not super fast, as we expect, actually. But this is common architecture, and when we develop distributed applications, and by the way, here you see the complexity increases more and more. But with distributed applications, the complexity increases again. So who of you develops distributed applications? Okay, all of the others, single node machines, right? Mostly monolithic applications. Okay, let's create a distributed application. So we start multiple processes of our application or a microservice in parallel because of a higher load. We want to scale horizontally. We need a distributed application. All of these application instances or microservice instances have a local cache. Now, let's change some data. So a user changes an object. The node stores the object back into the database system. What happens? Now this node and the database are in sync. The problem is that the database and all of the other application nodes are not in sync. So they, we have an issue here with our data state in the memory. This might be a problem sometimes. So how can we solve this problem? We can now put the cache between the application nodes and the database. When we do that, this would be a single point of failure. This is not great in the cloud, so we need a cluster. So we run a cache on its own machine, and to be able to scale the cache horizontally, we need a cache cluster. So, and this is a distributed cache. So, and the question is now, do we still need a local cache in our application nodes? So, it depends. So, it depends on your use case and your architecture. Are your application nodes or microservice nodes, are they stateless, stateful? So it depends on the use case and how you build the system. So sometimes you will use a local cache, and sometimes you don't need a local cache. For instance, if you use AWS Lambda, perhaps you don't need a local cache. Or it's because it has no state. So this is a common architecture for distributed cache, and if you use a local cache in your application nodes, mostly the distributed cache solution is able to update your local cache. It depends on the system and the solution you use. But this is important, and most modern products can update the local cache also. When the load goes up, then perhaps we need, we have more load on the database, of course. Then mostly we also need multiple nodes of our database system. So we also have to cluster our database system. So, and this is now a common architecture. We run 3 clusters for our scalable, horizontally scalable application. But now we are really able to scale out and scale in, hopefully. It depends on how you build your system. Because the idea is if the load goes up, then it scales automatically. If the load goes down, it should scale in automatically. But it depends on how you build the system, of course. Distributed cache mostly is used for websites, shop system. It's mostly uses key value structure, caching results. So these are the common use cases for distributed caches. And of course, reducing the load on a database. So actually, we should avoid hitting the database because the cache solution is faster, but it's again not that fast as we would expect, because between all these nodes are wire, and so this is not memory performance, but much faster than without caching, of course. Here are some products. So Redis is well known as distributed cache. Yesterday we had a workshop here, and the speaker explained Redis is not only a distributed cache, but it's known as a cache. Then, of course, we have InfiniSpan, Terracotta as cache, very popular. Hazelcast can be used as a distributed cache, and so on. There are so many solutions. You should check out which fits best for your use case. Then the question is, what is actually an in-memory data grid? So who uses in-memory data grids? Okay, not that much. Okay. In-memory data grid basically works fundamentally similar to a distributed cache, but in-memory data grid is also able to be used for computing, for distributed computing. So we have some computing functionality on top of distributing the data. So we add some more functionality, and then it's also distributed, of course, to distribute the data. And now with the in-memory data grid, we can distribute the compute capacity. And we also can distribute SQLs with the in-memory data grid. The architecture looks similar to a distributed cache, and this is the reason why most distributed caches are also, and at the same time, in-memory data grids. So when we have a look on the vendors, here we have actually the same vendors because they are at the same time in-memory data grids. Why should you use in-memory database? And what's the difference between in-memory database and a distributed cache or in-memory data grid? So in-memory database works a little bit different. So again, I like to have a look inside the database. Here now we move the database system into the memory, and we load all data in the memory and keep all data in the memory, and now we're able to execute all SQL queries in memory, and the in-memory database runs inside the application node. As a persistence, mostly the vendors they tell us to use the traditional database system as a backup system. Then you can run the in-memory database in memory, and you have your traditional database system as a backup. So it increases, of course, the complexity of your system, yeah, of course, you have multiple license fees to pay, but it can be an advantage because the in-memory database works pretty much the same as the traditional database, and this is can be an advantage. So it supports SQL, it works pretty much the same, administration is the same, and this is a big advantage for using in-memory database. But mostly in-memory databases are also used together with distributed applications, which means you cannot keep your in-memory database inside your application nodes. So it makes more sense to run the in-memory database as a separated in-memory database cluster between the application nodes and the traditional database cluster. So here we have pretty much the same architecture, but as I mentioned, the in-memory database is great if you have SQL experts and experts for relational databases or for column stores. Then perhaps in-memory database is a good fit for your solution. Here are some vendors. Of course, Oracle and SAP are the market leader for in-memory databases. But there are more and more databases coming up providing the same functionality. There is another interesting solution existing, and this is called system prevalence, and this concept was invented or is known for decades actually, and this is a very interesting functional principle, and this uses the Java power. So we wanted to know if Java is fast enough for in-memory computing, and I believe it's super fast and absolutely suited for in-memory data processing because of the JVM performance. We have the JIT compiler, and with GraalVM native images, we are now able to compile Java application into a native image, and this is also executed very fast. So Java is absolutely suited for in-memory data processing. Java also has a big advantage. All of these database systems out there, they introduce their own proprietary data structure or formats. Java actually has the best data structure that is existing, and we have object graphs in Java. Why are object graphs so powerful? The database vendors currently work on multi-model databases because with microservices, each microservice should have its own database. And now it depends on what the microservice is doing. It depends on its domain. So some use cases are suited for relational databases. Some use cases are more, are better if you use a time series database. For instance, if you have a sensor that delivers data all the time, so mass data, so perhaps a time series database is the best fit. But for some use cases, perhaps a key value store is better approach. With the Java object graph, we can cover everything because with the Java object graph we can store any object in object graph. We can use collections. We can create our own index. We can store in an object graph a JSON file, everything. So the Java object graph actually is already a multi-model data structure. What's about query language? Most of you, I guess, know the Java 8 Streams API. If you use Java Streams for searching object graphs, this is really powerful and really fast. So even if you search terabyte of data and complex object graphs with circular references in memory, it will take only microseconds. It's really hard to beat. Microseconds, which means it should be 100 times or 1,000 times faster than a comparable SQL query. Is this fast enough? I guess it's incredibly fast. So we have a great data structure. We have a great query language in Java. We also can use GraphQL. And now we have this system prevalence pattern that says, just keep your objects in memory. Don't care for money because memory becomes cheap in the future. So you can buy a lot of memory, put it in your machine, keep all your data in memory, query your object graph with Streams API, and you get the fastest application, the fastest system existing on the planet. Sounds cool. But what's about persistence? Yeah, persistence is also simple. Just serialize your objects to disk. This is really powerful if you run single node machines. So mostly it's okay for many use cases because the complexity is very low. If you can use this concept, then it's great. As a storage, you don't want to store your data in plain files. You can do that, of course, but perhaps it's not great because it's not managed. But now the cloud providers, they introduce cloud blob storages like AWS S3 or Azure blob storage or Oracle Cloud object storage. So all the cloud vendors provide binary storages, which are great for storing the serialized objects persistently. And why? It's because the cloud storages are full managed, so you get out backups automatically. They are automatically distributed, so they have automatically data center replication. So it's perfect. So, and it's high available, it's managed by the cloud vendor, it's cloud native. Perfect. So great combination. And let's have a look at the architecture. So which means now we have a Java application or a microservice written in Java. We keep the data in memory. We only have the JVM. We only have our classes. There is no more database model that forces us to adapt our object model to the database model. So super simple to use. No more object relational mapping, no more conversions. Just serialize your objects into a blob store. The problem here is you don't want to serialize the entire system state. And by the way, Project Crack does the same with storing the state of your JVM to get a faster restart of your JVM when you start your microservice. And then now we can start microservices in milliseconds. It's the same functional principle, but Project Crack just stores the state of your chit optimization. But in this case, we want to store the entire database. And this might be a problem because of it, depends on how big is your database, lot of traffic, so there are so many weaknesses of these concepts actually. Mostly this will not work in practice, and perhaps this is the reason why this concept is not that popular in practice. And now with the MicroStream open source project, we improve this system prevalence concept, we increase this concept, and we don't store the entire system state, we just store the changes. We just serialize the deltas on the object graph. And then this functional principle becomes super powerful. MicroStream is open source already, and it's integrated with Micronaut already. It comes with Helidon, so if you use Helidon or Micronaut, you have MicroStream under the hood anyway. And now I like to announce, especially here at Jfokus, that MicroStream becomes an Eclipse project this month. So great news. Oh, thank you. Cool. And by the way, for us as developers, we worked 20 years on Java, so distributing or contributing to open source projects, this is really great motivation, and to build something that is used by thousands of developers, this is fascinating, and this is great for the entire team, and we are super happy to build the application or software that is used by other developers in the community. You can find the code on GitHub already because it's open source already. You can download it via Maven, very easy because it's a Java library just integrated, and you can use it. It was built 10 years ago, so we built it when we saw that we were not able to improve the Hibernate tools. Then we tried this functional principle of system prevalence. 2 years later, we used this in practice. In 2019, we decided to launch MicroStream as a product. Now it's open source, and we're going to push the code to Eclipse. How does this work? The functional principle is really simple. Let's have a look inside the database again. So here we can see, of course, we don't use store procedures. We don't need the database system anymore because we believe everything has to be done by the Java business logic, concurrency and validation and so on. And we replace hibernate with MicroStream, so no more object relational mapping. Then we keep data in memory, which means data are already in memory, don't need a local cache anymore. We don't need a database system anymore because it's covered, all these functions are covered by the business logic. We only need persistence. That's everything. We don't need a query language. Java provides streams. We don't need data structure. It's object graphs. So we only need storage. With MicroStream, we can serialize data in any binary storage, plain files. We recommend blob storages, but you also can use a relational database because it can store binaries, basically. Perhaps it makes no sense, but basically it's possible. So no more conversion, no more object relational mapping, super fast queries, up to 1000x faster queries. Many databases are supported. It runs everywhere because it's Java. The only requirement is Java version 8. Now the latest version will support Java 11. It also runs with GraalVM native images. It runs also on Android. Here is a performance demo. Here are two applications running in parallel, 250 gigabyte database. It's a bookstore demo. You can find the code on GitHub. One application is built with a traditional JPA stack using Hibernate EH cache. It's a hot EH cache. And the other application is created with MicroStream as persistence. And you can see the query code. We use Streams API, and all queries are around 1000x faster, sometimes only 10x faster, sometimes more than 1000x faster. This is not MicroStream performance, this is the performance of the JVM, of course. And MicroStream adds persistence. So you can check out the code, implement your own queries, play around, and try to be faster with traditional databases. And you should do that because you should find out what fits best for your solution. So this is only an overview of in-memory technologies. You can also find a report, very interesting, in the internet. The preprint is free. You can download it for free if you like. This is very interesting. So they checked out and made a performance test in comparison to JPA. MicroStream is not only a serializer, so it's not Java serialization. We wrote a serialization from scratch that works fundamentally different from Java serialization. It enables you to persist any object, any complexity of your object graph, any depth of your object graph. You don't have to implement the interface serializable. You can serialize and store all Java types. This is very important. Don't need any annotations, no superclasses, very easy to use. We have an implementation for the JVM and for Android. We have a legacy type mapping that manages everything, manage the changes of your classes. So if your classes change, then MicroStream recognizes through runtime automatically that the object does not fit to your class, and then it handles this automatically. We have also a file system garbage collector because all objects are stored appended to the file storage, similar to event streaming, but we don't keep all objects in the storage. So with this file garbage collector, we remove the older and legacy and the corrupt binaries from the storage behind the scenes. Database connectors, and with the REST interface, you have access, or third-party applications can have access to the storage, and can have access to your data in memory. With GraphQL, third-party applications can have access to your data in memory. And we also provide a viewer where you can store through your storage data. And of course, native backup functions if you don't use blob storage. And also converter for CSV and other encodings. And on top of that, we provide MicroStream cluster, because MicroStream as it is today only runs on a single JVM, but most companies want to build distributed applications, and now with MicroStream cluster you can replace traditional application nodes or microservice nodes with MicroStream nodes. Because of we serialized data into S3, we don't need a database cluster anymore, so you can skip your database cluster. Because of your data already in memory, don't need a cache cluster anymore. So it saves lots of machines, reduces your complexity, and saves lots of money. Why? And it's because in comparison to database as a service, like PostgreSQL as a service, you save 99% storage costs when you buy AWS S3, for instance. So if you have 250 gigabyte and you have a small machine, it costs you from $300 up to $3,000 per year, PostgreSQL as a service. 250 gigabyte AWS S3 costs you $70 per year. So you can also save lots of cloud storage costs. There's also a valid architecture if you use stateless application or microservice nodes, then you can have access with REST to a MicroStream data provider cluster. This is a different architecture, but there are so many possibilities to build your architecture. All right, conclusion. In-memory computing is used everywhere. Java is so powerful, and we have so many technologies. In-memory data grids, distributed caches, this new system prevalence we working on. Java is fast enough for in-memory data processing. We have the best data structure, so database vendors working on multi-model databases, we have it already in Java. We have great query language. It's type safe. There are no SQL strings, something like that. It's super type safe, fully object oriented. So, of course, with all these technologies, you have challenges. And you have pros and cons. With MicroStream, it's the same, because you have to think different. There are no more SQLs. The DBAs, they hate it. But it depends on what you're doing. It depends on the use case and on your experience. We're Java developers. We like object-oriented programming. And if you like MicroStream, you can check it out, download it, follow our new Eclipse project, give us feedback, and if you have questions, you can visit our booth. We are happy for feedback. Yeah, thank you for joining my talk, and it was really a pleasure to be here in Sweden for my first time in Stockholm and at this fantastic conference. Thank you for having me. Have a great day. Do we have 1 minute for questions, perhaps? If you have some questions, of course, we can find us on our booth, but yes, please.
Yeah, I see some similarities with what Terracotta did a few years ago. Can you please tell me why this thing is different from Terracotta?
Yeah, so it seems similar to what Terracotta does. I cannot tell you exactly what they have done, what the similarities are between Terracotta and MicroStream, unfortunately.
Okay.
Yeah.
Okay, and the other thing is
Yeah.
that, yeah, you said probably a DBA hates something like this,
Yeah.
but just because you are serializing objects in a binary format,
that's it, because we create our object model with Java classes, just POJOs, and this is mostly not readable for DBAs. We have a graphic user interface where you can browse through your storage data, but you cannot send an SQL to the storage because there is no more database system behind the scenes. It's plain binaries, and this is why database administrators mostly say, that's not so cool. It depends on your team. Yeah. Sure. Yeah. Yes. Okay. I'm sorry for that. Thank you.